Hey everyone, today we're going to take the things we've been talking about in the last few sections and we're going to start putting it together and see how it all fits together. Remember, we originally started by talking about a sequence, and a sequence here, we use this kind of notation. A sequence is just a list of numbers, right? And you can number them any way you like, but normally we start by numbering them from 1, and so we get a sub 1 and a sub 2 and a sub 3, and we just get this list of numbers. And so out of that sequence, and you've really got to be clear on what these things are because these are all going to start interacting today. So starting from that sequence, we added together the different terms in the sequence, and if we do this forever, we get what's called an infinite series. And this infinite series is written out here, right? I can write it using the sigma notation that we have from Calc 1. It just says take every value of I from 1 to infinity, so keep going forever. And so what I've shown here is that any term you kind of name is going to be in the sequence, in the series, because you can have A1 and A2 and A3 and A4, and they're all going to be added, and so is A5 and A6, and for any n, it's going to appear somewhere in the series, right? So A sub n is going to be there, and then A sub n plus 1 and A sub n plus 2, and so, I don't need this, I'm just kind of showing that all of the terms are in there. And then we took that and we used it to define what we called the nth partial sum. We called that S sub n. And the nth partial sum gives us the sum of the first n terms. And however the terms are numbered, you might write it in different ways. So if your sequence, if your sequence starts at 0, and so you're adding A0 and A1 and A2, then the first n terms is going to be up to n minus 1. So what I'm saying here is, let me just put that somewhere else, S sub n is equal to A sub 0 plus A1. This is n terms, right? So if n is, let's say, 3, the first 3 terms are A0, A1, and A2. I stop at the n minus 1. So it just depends how you numbered it, because this is a series where I'm starting from 0 and going to, in this case, n minus 1, and that gives me n terms. So whatever S sub n is, it's going to, however you've labeled these terms, that label, that index, remember we called these numbers down here the index, they don't really affect the actual values because they're just labeling, what term it is in the sequence, because we had this sequence of numbers and we just label them in some order. Okay, so if we add up the first n terms, we get the nth partial sum. And so we can play some fun games like this, right? So for example, the nth partial sum I've got written there. And I could write out the n plus 1th partial sum, right? It's the sum of the first n the n plus 1 terms. So there's the first n terms. And then the n plus 1th partial sum is just adding the next term on. So one thing you could notice from this is if I took the n plus 1 partial sum and subtracted the nth partial sum, well, I'm subtracting all of these terms. And what we're left with is just the n plus 1th term. And so, we can extract terms and things out of this, terms from the original sequence. So one way of thinking about this is the partial sums themselves are a sequence, right? And we talked about this last time, but the partial sums themselves are a sequence because each time we add another term, this is going to get bigger if the thing we're adding is positive. And so our last idea in the previous section was that this infinite series will converge if the partial sums converge. In other words, if this sequence of partial sums, I'm going to list out all the partial sums, if they get closer and closer to a number, then I'm going to say that the series itself converges. In other words, I'm saying the infinite series converges if the sequence of partial sums converges. I'm saying that the limit as n goes to infinity of S sub n converges to some finite number. That's what I mean by the sequence of partial sums converging. And we talked in section 11.1 about what it means for a sequence to converge. And the sequence this time is the sequence of those partial sums. So there's several items going around here, right? We've got the original terms, they make a sequence, that's a list of numbers at the top. We then add them together, and if we only add some of them together, we get the nth partial sum. And if we add the first one, then the first two, and then the first three, then I've built a new sequence, and that new sequence is the sequence of partial sums. And the limit of that sequence tells us about the convergence of the series that we were thinking about. In this section, we're going to concentrate on series that have positive terms. And so every one of the original sequence here was every number is positive, which means that each time I add a new number, the value is going up, which means this sequence of partial sums is strictly increasing because each time I add a new number, look, I went from A1 to A1 plus A2. I went from A1 plus A2 to adding a3. Each time I add that new number, I'm adding a positive value. So S sub n is an increasing sequence, right? And that's the key idea we're going to have as we move forward. Because all of the terms are positive, every time we add a new term, the value gets bigger. And so what we can immediately say, using the ideas from 11.1, is if we're adding up positive values, if every term that we're adding up here is positive, then the partial sums can either be bounded above or not bounded above, right? So if they're bounded above, what that means is if I were to look at the partial sums, there's the n value, there's the Sn value, and here's my bounded above idea. And again, go back to 11.1 if you want to have a recollection of what this means. But if it's bounded above, it means it kind of horizontally, it's got a line above it that it never gets to, right? It approaches, or asymptotes maybe to that value, but it never crosses that value. It never gets bigger than that value. And since this is the values of the partial sums, and we know that those partial sums are increasing, they must get bigger with time. If they're bounded above, then they must converge to some value. And we had a theorem that said that in the previous section. So to show that this sequence the series that we're interested in converges, it's enough to show that the partial sums are bounded above. And of course, if they're not bounded above, that means the partial sums are increasing, but they just keep getting bigger and bigger and bigger and bigger, then that sequence must diverge. Because the thing that's getting bigger and bigger and bigger is the terms as we're adding them together. So in other words, they're getting bigger without bound because they're not bounded above. So those ideas, let's use them to kind of look at an example. We want to decide if this infinite series converges or diverges. And if I start writing out the infinite series, when n is equal to 1, we get 1 over 1 squared, then we get 1 over 2 squared, and then we get 1 over 3 squared, and then we get 1 over 4 squared. And so this is our infinite series, right? It goes on forever. And the argument we just made was we can decide about the convergence or the divergence of the infinite series by looking at whether the partial sums are bounded. And now if you think about the partial sums here, the first partial sum is just 1, the second partial sum is 1 plus 1 over 2 squared, the third partial sum is 1 plus 1 over 2 squared plus 1 plus 1 over 3 squared, and so on for S4, and we can continue in that way. So the nth partial sum just looks like that. So what I want to do is interpret this actually as a geometric object, as a picture. So let's go to the next page and draw a graph. So on this graph, I've drawn the graph of y equals 1 over x squared, right? Which corresponds to the thing we're adding up here. Because the nth term in this sequence that we're adding up is 1 over n squared. So this is, if we think about this as being generated by a function, then that function is 1 over n squared for f of n, or 1 over x squared for f of x. We've got a function here that's generating those values. Because in other words, when I plug in 1, I get this value, which is, what's that value? That value is 1, because I plug 1 into this. And when I plug 2 into the value here, I get 1 over 2 squared. Right? And when I plug 3 into the function here, I get that point. So I'm calculating this point. This is 1 over 3 squared. When I plug 4 in here, I get this height, and this height is 1 over 4 squared. And so you get the idea. So the question is, what's the area of this? Well, it's 1 high and 1 wide, so that has area 1. What's the area of this rectangle? Well, this is now, the height is determined by the value of the function there. The value of the function is there is 1 over 2 squared. So it's 1 wide and 1 over 2 squared high. What's the area of this rectangle? Well, that rectangle is going to be 1 over 3 squared high, and it's 1 wide, so the area is 1 over 3 squared. And the area of this rectangle is 1 over 4 squared, right? So this is 1 over 4 squared. So what's the area, if I kept doing this, what's the area that I would get in total as I continue to play this game and draw these rectangles in and then add up the rectangles? You know, this sounds like a Riemann sum, right? So I'm continuing to find the areas of all of these rectangles, and as I keep doing it, what I get is the series that we want. In other words, this entire shaded region under the rectangles is going to add up to give us this series that we want. In other words, it's going to equal this entire sum, because I'm adding 1, and then I'm adding 1 over 2 squared, and 1 over 3 squared, and 1 over 4 squared. This is going to be 1 over 5 squared, 1 over 6 squared, 1 over 7 squared. You get the idea. But notice that that value is below the graph, right? So if I knew how to calculate, let's say, if I knew how to calculate the integral between 1 and infinity, and then I add 1 on. So the area between 1 and infinity below the curve 1 over x squared, that area is going to be all of this plus the shaded rectangles, right? So all of this plus the shaded rectangles, and then I'm adding the 1 on, and adding the 1 on is given this. So what I'm doing is I'm taking this area, this first rectangle, and then I'm integrating from 1 to infinity to give me the rest of the area under the curve, which is the rectangles, plus that little bit at the top. So whatever it adds up to, it's going to be bigger than the value of the series. So when I add up the terms in the series, when I add up 1 over n squared from n is equal to 1 to infinity, what I'm going to get is a number that's smaller than the value that comes out of that integral, right? Because the value that comes out of that integral is going to be all of this, right? The bit at the top as well as the rectangles. So all of this, and then I'm adding 1 to it to give this piece. So that's more than the area that's just under the rectangles, because I'm adding all of these little pieces at the top on, right? This is bigger than the area that's given under the rectangles, which is the values of the series. So what that means is if this integral actually converges, in other words, it has a finite value, then the series is bounded above. In other words, the partial sums are bounded above. And if the partial sums are bounded above, then that series converges, right? Because it's always every nth partial sum is less than some finite number. And so that gives us what we need to know. And in the previous sections, we worked out how to do improper integrals like this. So remember how we do that. We replace that infinity up there because it makes no sense in an integral, definite integral. We replace it with a finite value r, and then when we're done taking the integral, we'll take the limit as r goes to infinity. And the integral is just going to be 1 over x, and we're evaluating that between 1 and r, and plugging that all in gives us this, and as r goes to infinity, then 1 over r must go to 0, and so this whole thing goes to 1. And so what we found is that this is actually equal to 1. So we found that the series we're interested in adds up to some value that's less than 2. In other words, if I was going to be more technical here, and I'm being a bit loose with it, what I'm saying is the nth partial sum is going to be less than 2. So what we've got is this thing is bounded, right? Because this thing is bounded, it must converge. So it converges to some value. It doesn't necessarily converge to 2, because I don't know that 2 showed up in my calculation, but there's no reason that this series actually needs to converge to 2, but it's going to converge to some number less than 2. And that's the key idea here. And what we've seen, so we've seen two important things. The first one is that the sum of 1 over n squared, 1 from n equals 1 to infinity, that converges. And that's a really important fact. So I want you to remember that fact, bury it into your brain. The sum of 1 over n squared from n equals 1 to infinity, that converges. It gives us a finite value. I don't know what that value is, but it is a finite value it converges to. So just to summarize, what we did was we built this inequality based on that picture. Based on the rectangles, we built this inequality. We found that the value of this integral was 1, so we got this was 1 plus 1. So this entire infinite series has to be less than 2. From our picture, it seemed reasonable, right? And so what we did was we said that this sum of 1 over n squared from 1 to infinity, it converges because this thing converges. And you might ask, well, where did these things come from? This was our nth term, right? The nth term was 1 over n squared, and we thought about that as f of n, and then that led us to use this integral. And where did the 1 over x squared come from? Well, that was f of x, because the term told us what the function was. It's 1 over whatever squared. So if I'm integrating 1 over x squared. And so the term is giving us the function that appeared here. In the second part of my statement here, I'm saying that if this integral had have diverged, we could have concluded that 1 over n squared diverged. And just quickly, why that would be, instead of building rectangles that use points on the right, we could have built rectangles that use points on the left. So we could have built these rectangles. And notice that this first rectangle has area, well, this is going to be 1 because that's 1 and 2 and 3 and 4. And so if I start adding up the area of these rectangles, that first rectangle has area 1. The second rectangle has area, well, the height here is 1 over 2 squared. So the area of the rectangles that you see there is exactly our series. But notice that in this case, our infinite series, but notice in this case, that's going to be bigger than that integral from 1 to infinity under the curve itself, because the area under the curve itself is just the white part here. But by drawing slightly different rectangles, we can see that we can build this inequality where the infinite series is actually bigger than that as well. Now, I've dropped this term, which is why I can do this. You've got to think carefully about the areas. But the point is, if this had have gone to infinity, if that had have diverged, and this is bigger, then I'd have to conclude that this diverges too. And so this leads us to what we call the integral test. And so the integral test is very much the idea that I just used. If you've got this sequence that you're adding together to get an infinite series, and the terms in that series are positive, and they're decreasing, and they're continuous. So we need all of those things. Now notice that that was true of the example we did, because the terms in the sequence were generated by a function. The values in the sequence, the a sub n's, were given by 1 over n squared. And so those values were getting smaller as n got bigger, right? They're the points along that smooth curve. So there's our n-axis, and there's 1, and there's 2, and there's 3, and so on. So these are positive numbers. They're definitely decreasing. 1 over n squared is continuous for all n bigger than or equal to 1. That's true. It's continuous everywhere that n is, or x is bigger than 0. So for the continuous function, it's continuous definitely from 0 onwards, not including 0. But what the integral test tells us is, if that integral converges, then the series of those terms built from that function also converges. But if that integral diverges, then the series built from those things also diverges. Let's do an example, because we've already seen one case. Let's do another example and see what happens. So our first example involves this harmonic series that we've seen before, where we add together the sum of 1 over n from n equals 1 to infinity. So you get 1 plus a half plus a third, and so on. Our first ideas, or our first job when using this, is to make sure we have a function and to make sure the function satisfies the conditions of the integral test, because otherwise we can't use the integral test. And in this case, our a sub n is just 1 over n, right? And so that's the function that's defining what's going on here. And so the continuous function we're going to be interested in integrating is the function 1 over x. And what we need to know is that positive? Well, it's definitely positive. I'm going to use x rather than n, but it's definitely greater than 0 for all x greater than 0, right? And all we needed was x bigger than 1, so that's okay. So it's definitely true when x is bigger than 1 that this function is greater than 0. Is it decreasing? And it's definitely continuous, right? So let me add that as well. It's definitely continuous for all values of x greater than 0. So definitely true for all values of x greater than or equal to 1, because that's our condition. The last one, though, is it decreasing? We have to make sure it's decreasing. And one easy way to work out if the function's increasing is to look at the function of real numbers, the continuous function. So remember, we're swapping here between two different kinds of functions. We've got this function f of x, and it's defined for all values of x. And then what we've got is this function f of n. Well, we're applying the same function to the values n, by which I mean the integers, and so that's just producing these values, right? F of 1, f of 2, f of 3, f of 4. So there's f of 1 and there's f of 2. So when I'm using the n values there, I'm thinking about discrete numbers, just a bunch of points. When I'm talking about f of x, I'm thinking about a function that's continuous, and so it's differentiable, and in this case it's minus 1 over x squared, and that's always negative because x squared is always positive, so that's negative. And so if f prime is negative, then we can say it's decreasing, because a negative derivative means a decreasing function. So this is the best way to show that things are decreasing. We've already showed it's positive, we've already showed it's continuous, now we see it's decreasing because the derivative is negative for all x greater than or equal to 1. That's all we care about. It's true everywhere else except 0, because it's not defined at 0. It's true everywhere else. It's a decreasing function for all x, but in the domain. But we only care about x greater than or equal to 1. Okay, so now we've checked the conditions. We've got a positive function, we've got a decreasing function that's continuous on x is greater than or equal to 1. So what our test tells us is to evaluate the integral from 1 to infinity of f of x. And if it converges, so does the series. If it diverges, so does the series. And remember, this is an improper integral, so we have to replace it with an r, and then we evaluate that integral. And that integral is just the natural log of the absolute value of x, but evaluated between 1 and r. And so what we end up with is the natural log of r minus the natural log of 1. Well, the natural log of 1 is 0, you know that already. but it doesn't matter. It's a finite value. And I could put absolute values here, but r is going to infinity anyway, so it doesn't really matter. The point is that this is going to be infinite because the natural log, the limit as x tends to infinity for the natural log, goes off to infinity, because if I draw the natural log, it looks something like this. So our natural log function is divergent as x goes to infinity. This integral, therefore, diverges because it does not have a finite value. The limit does not converge to a finite value. The limit diverges, the integral diverges. Therefore, by the integral test, this harmonic series diverges. And that's another really important result. The harmonic series is a fundamental series that we care about, and it diverges. What that means is the terms aren't getting small enough, quickly enough. So let's have a look. Remember what we found? We looked at this harmonic series and we found that it diverges. I left the letter out. Harmonic series. And what that means is this does not converge to a finite number. As I keep adding values, this list of numbers, this series just gets bigger, and the partial sums, I should say, just get bigger and bigger and bigger and bigger without end. Whereas when I add up 1 over n squared as opposed to 1 over n to the 1, when I add up the terms 1 over n squared, these numbers are getting small enough, fast enough, that we in fact showed that s sub n was less than 2 for all values of n. So in fact this converges to a finite number. This must give me a finite number. I don't know what it is, but I know that it has to converge to some finite value. Whereas this goes off to infinity. It diverges. This first list of numbers, as I keep adding up, they just get larger and larger and larger without end. But this list of numbers, try it, grab a calculator, start adding these. You'll see that it stays below 2. It very quickly, it climbs at the beginning. You've got 1, then you add a quarter, and then you add a ninth, and then you add a 16th. But the size of the thing you're adding slows down often enough, or quickly enough, that series actually converges. And these are two important examples of what's known as p-series. Let's look at the general case. So what we want to do is decide what values of p this series converges for. And just writing out the series, we're talking about something like this. So you can immediately see, I hope, that if p is negative, things aren't going to converge, right? Because if I start adding up the values when p is, let's say p is minus 1, then what we've got is the sum of the terms n, which is 1 plus 2 plus 3 plus 4, and so on. So that's got to get bigger and bigger and bigger. So in that case, the limit as n tends to infinity of this nth partial sum has got to go off to infinity. As I keep adding more terms, it just gets bigger and bigger and bigger. And this is true for any value of p that's less than 0. So this is only possible if p is bigger than 0. So let's start with that assumption. We'll take p bigger than 0 and we'll ask, what values is this thing going to converge for? So I don't think you're going to be surprised here that we're going to use the integral test again. And so looking at the terms of the series, they're 1 over n to the p. P is a number bigger than 0. So the function I need to think about in the integral test is 1 over x to the p. Now, if x is, that's horrible, if x is greater than or equal to 1, then hopefully it's obvious to you that if we're just taking powers of that, it's got to be greater than or equal to 0. Right? In fact, it's got to be, well, it's going to be greater than or equal to 0. If I give you a positive number, taking a power is not going to change it from being a positive number. So f of x is still going to be positive. That's good. And f is definitely continuous for all x bigger than 0. So it's continuous for all x bigger than or equal to 1, because these functions we deal with are continuous on their domains. We remember that from Calc 1, hopefully. And the derivative of this function is going to tell us whether it's increasing or decreasing. And the derivative is going to be p over x to the power of, well, this is the same as x to the power of minus p. So negative p comes down. I reduce the power by 1. And so this becomes a bigger power when I put it back in the denominator, right? So just rearranging that, you can see it looks like that. P is positive. X to the p is positive. So this has to be negative, right? Because we've already said that p is positive and we expect that x to the p plus 1 is positive. So this whole thing must be negative and therefore f is decreasing. And that's what we wanted, right? If the first derivative is negative, then f is decreasing. And it's decreasing everywhere, but in particular, it's decreasing when x is bigger than or equal to 1. And so this satisfies the requirements of the integral test. So the integral test says, think about the limit, of 1 over x to the p from 1 to infinity. And so we just integrate 1 over x to the p. Replacing as an improper integral, replacing the infinity with a limit, we get x to the power of minus p plus 1, and we divide it by that number. And I really need to note that p is not equal to 1, because otherwise I'd be dividing by 0. But that's all right, because we've already done that case. That's the case of the harmonic series. We know that one diverges. So plugging in those endpoints, what we get is this limit, where I've just factored out the 1 over minus p plus 1, because it's not really important. P is a fixed number. We know it's not 0, so I don't have to worry about division by 0 there. And we're left with, when we plug in x equals r and x equals 1, we're left with this calculation. And so the only question is, what happens to this term as r goes to infinity? Well, as long as that r is in the denominator, then that thing has to go to 0, right? We can conclude that that thing in the purple there must go to 0 as long as r is in the denominator. Well, for r to be in the denominator, then the power must be positive, right? Because if that's a negative power, like we had before, imagine that was a negative power up there. Well, that's really r squared. And as r goes to infinity, r squared does not converge. So for this to truly be in the denominator, I must have a positive power here, not a negative power, because if it's a negative power, I can just flip the fraction. So I need p minus 1 to be positive. In other words, I need p to be bigger than 1. So as long as p is bigger than 1, this thing goes to 0 because it's of the form 1 over infinity. It's not indeterminate. It goes off to 0. But if p is less than 1, in cases like this, maybe p is negative 2, well, we said it also could be positive. But sorry, if p minus 1 is less than 1, let me say that again. If p minus 1 is less than 0, in other words, p is less than 1, then it's going to diverge. Because, for example, if p is a half, then this is r to the power of minus a half, and that's really the square root of r, and that will diverge as r goes to infinity. So this one will diverge. It'll go off to infinity. And we know p is positive, so it diverges like that. And what that leaves us with is that the integral from 1 to infinity, which is actually equal to those values, this term is going to go off to infinity if p is less than 1, but as long as p is bigger than 1, that'll go to 0, and so it'll converge. So it converges, that whole integral converges when p is bigger than 1, and it diverges when p is less than 1. And that includes the cases where p is negative, because we know if p is negative, that will diverge, because we talked about that earlier. And so this kind of conclusion is what we get from the integral test. And what this result gives us is what is known as the p-test, because the convergence of that integral is linked to the convergence of the corresponding series. And so this series converges when p is bigger than 1 and diverges when p is less than 1. Oh, and we also know that if p is equal to 1, that's the harmonic series, it diverges. So we can add the equals to here, because the harmonic series is when p equals 1, and we've already showed that diverges. So this statement at the bottom here is what's known as the p-test. And here it is. It simply says the infinite series, that's the sum of 1 over n to the p, converges when p is bigger than 1, and it diverges otherwise. So it diverges when p is equal to 1, it converges when p is less than 1, but positive, it diverges when p is less than 1, when it's equal to 1, and when it's negative as well. So this gives us another way of quickly checking the convergence of series, because we just worked really hard to use the integral test. The integral test takes a lot of work, but once we can use it to get this kind of result, we can use this quickly on series that we're interested in. So let's look at a couple of examples. Here's the first one. We've got an infinite series that has fourth powers in the denominator there. So we're going to have 1 over 1 to the 4, and then 1 over 2 to the 4, and then 1 over 3 to the 4, and so on. So this is a p-series with p equals 4. And 4 is bigger than 1, so it converges. So the series converges. Right? That's the key idea. We look at this, we say this is of the form of a p-series. P is 4, it's bigger than 1, we're done. Here's another example, a series that has terms of the form 3 over n root n. This is not a p-series, but we could use the linearity. If this series converges, we know it's going to converge to 3 times 1 over n to the power of something, I can factor the 3 out. In other words, we had a theorem in the previous section that said linearity lets us bring constants out. So this is 3 times n to the power of, well, that's n to the power of 1, and it's multiplied by n to the power of a half. So this is overall n to the power of 3 halves from 1 to infinity. In other words, if I wrote that out, all I've got is the 3 out as a common factor, and then I'm doing this summation in here. But this is a p-series, right? This is a multiple of a p-series. It's a p-series with p equals, well, 3 over 2. So not including the 3, just looking at this piece, I've got a p-series, and p is 3 over 2, and that's bigger than 1, so this series converges. Right, and this is the care you should take when you use these theorems. You should check all the conditions like I did in the integral test. You should make sure that you're actually dealing with a p-series. A p-series does not have a 3 there, so the 3 should be factored out the front, and you should think about the p-series part of it. And so we looked at the p-series part, and it converges, and then looking back in the previous section, we can use theorem 1 and say that the theorem we were actually asked about converges as well. Right? Because this is 3 times the p-series. And theorem 1 back in section 11.2 said if a series converges, then any constant multiple of it will converge. So I'm using 2 things here. I'm using the p-series test, this theorem 3, and then I'm putting it back to the idea of linearity for these convergent series. So you should do that. You should split it into, I'm never going to call this a p-series because really it isn't. It's 3 times a p-series. So we should be really careful. And when I'm grading things in these sections, I'm going to be looking that you're checking the criteria and you're clearly identifying what p-series are. And you're telling me what p is, and you're telling me why it converges, right? In this case, p is 1.5. That's bigger than 1, and so therefore the p-series converges. Your answers should include that argument because that's the key to what's going on. And so if you just answer a question that says, a question like this by saying it converges, you'll get very few points because you need to tell me why, and you need to argue through logically using these ideas. So we really have seen a lot today. We've seen a bunch of new theorems and ideas. We're going to see a lot more of these. Practice using them now. I will see you soon. Come talk to me in Zoom office hours if you have questions. Have a great day.